Hello, 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 and welcome back to Shiksha DaCosta. Today we're going to review our unit on exponential relations. So in this unit, we demonstrated an understanding of exponents, we connected the numeric, graphical, and algebraic representations of exponents, and we solved problems using exponential relations. And we had to do a lot of things to get there. We had to determine the meaning of negative and zero exponents. We evaluated exponents that have integers, exponents, and rational bases, so negative numbers in their exponents. We figured out what that means, as well as when the base is a rational number of fraction. We then determined the rules for simplifying exponents, like multiplying and dividing powers, and the rules involving a power of a power. And that was using the algebra of exponents, and from there we moved on to the graphs. We graphed simple exponential relationships. We described the connections between their different representations in tables of values, graphs, and algebra. And we found the differences between exponentials, linear, and quadratics by making comparisons with their table of values, their algebraic representations, and their graphs. Finally, we used secondary source or primary source data, graphed it, and looked at some of the characteristics that popped up from that graph. From there, we started to ask questions, pose problems, and then solve those problems when those situations involved exponential relationships. In our first lesson together, we found out about exponent laws. So we saw that when we're performing operations that involve powers with the same base, we can use some tricks. For example, when we're multiplying two powers that have the same base, we keep the base the same and we just add the exponents together. When we're dividing two powers that have the same base, we keep the base the same and we subtract the exponents. That is the quotient law. The power law says that when the base of a power is a power itself, we could just multiply the two exponents together, and that simplifies it there. And a related rule is the power of a product of exponents, which says that when the base of a power is a product of two powers, just multiply the exponents by each of the outer exponent by each of the inner exponents, sort of like just the distributive property from linear algebra. And then we learned about negative and zero exponents. If you have a negative exponent, what you can do is imagine that if you have a negative exponent and an integer base, it's equivalent to the reciprocal of that base to the opposite exponent. So b to the power of negative n is equal to 1 over b. And the reason for that is b is actually any number is the same number over 1. And so what I did here is I flipped the numerator and denominator into its reciprocal. That's what a reciprocal is. It's a flip of the numerator and denominator. And then I also changed the exponent into the positive number. Another way to look at that would be to take this and move it into the denominator, or in other words, take this and move it into the numerator if it's already in the denominator. When you're simplifying algebraic expressions that have exponents in them, it's best practice to make sure that your final answer has only positive exponents. Zero exponents are super easy. Anything to the power of 0 is equal to 1. From there, we looked at the graphs of exponential relationships, and we saw that the graphs sort of look like this, where they're very flat on one end, and they're very steep. They very quickly increase at the other end. If the base of the graph is a number that's greater than 1, it's increasing when you go left to right. And if it's between 0 and 1, it's decreasing. It's decaying as we go from left to right. The algebraic form, the equation that would create this graph, is y equals a times b to the power of x, where b is any positive number and a is the initial value. That's where the graph starts. Now, every time we increase x by 1, the y value, whatever we had previously, gets multiplied by the base one more time, because that's what an exponent is, right? It's telling you how many times to multiply by b. If it's 0, then b to the power of 0 is 1, which means we'll be left with a times 1, or just a. And when x is 0, then we are exactly here, right? We're always at the y-axis. And for that reason, the y-intercept of any exponential relation is always this value here, a. Exponential relations have constant first ratios. And that means that when we're looking at a table of values, right, when you divide two consecutive y values, you always get the same ratio. So 9 divided by 3, 27 divided by 9 is 3, 81 divided by 27 is 3, 243 divided by 81 is 3. The equation, if you're looking at the equation of an exponential relation, then the variable will always be in the exponent. The independent variable, which is usually x, is in the exponent, not in the base. That's what makes it an exponential relationship. In our last section, we talked about how to apply exponential relations, and we saw that they happen all the time when things are increase or decrease by a percentage or by a factor. Exponential decay happens when the value is decreasing, and an example of that is an item cooling to room temperature, the intensity of light as it goes through a glass or as it goes through water, or the mass of a radioactive isotope. And in that case, it looks kind of like this, where the dependent variable, which is usually y, it will approach, but it will never actually reach a lower limit, whatever that number is. In this case, it's 20. Exponential growth is the opposite. It's actually growing when you go from left to right, so it's actually increasing exponentially. And examples of that include investments, debt, bacterial growth, and populations. The equations of exponential growth and decay are the same as the equations of exponential relations, right? Y equals a times b to the power of x, except b is equal to 1 plus or minus r. Plus if it's a growth rate, minus if it's a decay rate. And that r value, that's the rate as a percentage, we convert it into a decimal when we plug it back into here, and then we do 1 plus that number, and that's our base over here. That rate is usually expressed as a percentage for that reason. So for example, here we see the value of something growing according to the value of something growing every year exponentially. We can see that it starts really low and the graph is really flat on one side, and then it increases very quickly as as the years start increasing. When a situation involves an exponential relationship, you can use a graph or an equation to find out more information about it. To use a graph, all you have to do is find the value of the independent variable that you're looking for, go up from there, and until you touch the actual curve, and then go horizontally from there until you find a value of the dependent variable to use. And that will be the output. So after 37 years, the value of this, whatever we're measuring, was about $3,500. Now, this is not the best way to find an output with an exponential relation. It would be way better to use an equation where you can just plug in the value of x. So if this was our equation, we could just plug in 37 and get the exact number instead of trying to fiddle with a graph. And that was this entire unit. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.